Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with a focus on networking. Today, we're going through a detailed, real-world example of setting up Private Service Connect. Our fictional scenario involves Dataflow Analytics, a SaaS company that provides real-time data processing services to enterprise customers. They need to expose their service privately to TechCorp, one of their enterprise clients, without opening up their entire network. Dataflow Analytics runs their service in Google Cloud Project Dataflow Prod 1234 in the U.S. Central 1 region. Their service consists of a Kafka cluster and processing engines running behind an internal TCP load balancer on port 9092. TechCorp wants to connect from their GCP Project TechCore Data 5678 to consume this service. What makes this scenario interesting is that both companies have strict security requirements. Dataflow can't expose their service to the internet, and TechCorp can't peer their VPC due to overlapping IPs with other partners. Private Service Connect is the perfect solution. Let's walk through every single step, command, and potential issue they'll encounter. Let's start with Dataflow Analytics setting up their infrastructure. They already have their Kafka cluster running in a managed instance group across 3 zones in US Central 1. The instances are in the Dataflow backend subnet with an IP range of 10.10.0.0/24. They've configured an internal TCP load balancer named Kafka ILB that distributes traffic across these instances. Before they can create a PSC service attachment, they need to prepare a NAT subnet specifically for PSC. This is a crucial detail, as PSC requires dedicated subnets with a special purpose flag. These subnets provide IP addresses for the PSC infrastructure to establish connections. The subnet must be at least a /29, giving 8 IP addresses, though Google recommends a /28 or larger for production. Dataflow's network architect, Sarah, creates the NAT subnet using the command all-show. She chooses 10.10.100.0/28, which is outside their main service subnet range. This gives them 16 IP addresses for PSC connections, allowing up to 16 simultaneous consumer connections. Each active PSC connection consumes 1 IP from this range. One important caveat: once you create a PSC NAT subnet, you cannot delete it if there are active service attachments using it. You also cannot modify its purpose. Sarah documents this carefully in their runbook, knowing they're committed to this IP range for PSC. Creating the service attachment. Now Sarah creates the service attachment. This is where things get interesting, with several decision points. First, she must choose the connection preference: accept automatic or accept manual. For a production service with paying customers, she chooses accept manual to maintain control over who connects. The service attachment creation requires the forwarding rule name from their internal load balancer. Sarah runs the G-Cloud Compute Forwarding Rules List command to get the exact name, which is Kafka ILB Forwarding Rule. She also needs to decide on connection limits. Since they're starting with enterprise customers, she initially sets a limit of 10 connections. An important detail many people miss is that the service attachment name becomes part of the resource path that consumers will use. Sarah chooses Kafka Streaming Prod as a clear, professional name. The full path will be project/dataflow prod 1234/region/is central 1/service attachments/Kafka streaming prod. She will need to share this exact path with customers. After creation, Sarah monitors the service attachment status. It should show as active within a minute. If it stays in creating or shows failed, it usually indicates issues with the underlying load balancer. She verifies the ILB is healthy and has active backend instances before troubleshooting further. On TechCorp's side, their cloud engineer Mike needs to set up the PSC endpoint. TechCorp's VPC, TechCorp Production, uses an RFC 1918 IP range, which overlaps with several partner networks. This is why they love PSC's IP independence. Mike needs to choose an IP address for the endpoint from their existing subnet. Mike selects 192.168.10.100 for the PSC endpoint, documenting it in their IP address management system. He first reserves this IP address to ensure it won't be accidentally assigned to a virtual machine. This is a best practice. Always reserve the IP before creating the PSC endpoint to avoid conflicts. An important consideration is that the endpoint IP must be in a subnet in the same region as the service attachment. Since Dataflow's service is in US Central 1, Mike must use a subnet in US Central 1. If TechCorp only had subnets in US East 1, they would need to create a new subnet in US Central 1 first. PSC does not work across regions. Mike also needs to plan firewall rules. Even though PSC provides network isolation, TechCorp's applications still need firewall rules to reach the endpoint IP. He will need an egress rule allowing traffic from their application servers to 192.168.10.100 on port 9092. This point often trips people up, as they assume PSC bypasses all firewall rules. The connection request process. Mike creates the PSC endpoint forwarding rule, which automatically sends a connection request to Dataflow. This is where the accept manual setting becomes important. The connection enters a pending state, waiting for Dataflow's approval. Mike can see this status when he describes the forwarding rule. The forwarding rule creation is straightforward, but Mike must ensure he has the exact service attachment path. Any typo in the project ID, region, or attachment name will result in an error. He carefully copies the path that Sarah provided. project/dataflow prod 1234/regions/US Central 1/service attachments/Kafka streaming prod. Once created, Mike immediately checks the connection status. The PSC connection status will show as pending because Dataflow chose accept manual for their service attachment. This is expected behavior. It means the connection request has been successfully sent and is awaiting approval from the producer side. While waiting for approval, Mike documents the endpoint configuration for TechCorp's application teams. He notes the IP address, 192.168.10.100, port 9092, and creates a runbook for troubleshooting connection issues. He also sets up monitoring to alert when the connection status changes from pending to active. On the Dataflow side, Sarah receives an alert about the pending connection. She can see the request by describing the service attachment. The output shows the TechCorp project ID and the forwarding rule details. This is crucial for security. She can verify this is actually TechCorp and not an imposter before approving. Sarah has several options for accepting the connection. She can accept individual connections using the G Cloud Compute Service Attachments Update command with the Add Consumer flag, or she can add the TechCorp project to an accept list for future automatic approval. For this first connection, she manually approves it to maintain full control. Here is a critical detail. The approval must specify the exact forwarding rule path from the consumer. Sarah must use project/techcore data 5678/regions/is central 1/forwarding rules/Kafka PSC endpoint. Any typo here will fail silently, and the connection will remain pending. She copies this directly from the pending connections list to avoid errors. After approval, the connection does not become active instantly. It typically takes 30 to 60 seconds for the status to change from pending to active. During this time, the PSC infrastructure is establishing the secure connection between the networks and allocating an IP from the NAT subnet. DNS, configuration and application integration. TechCorp wants their applications to use a friendly DNS name instead of the IP address. Mike creates a private DNS zone in Cloud DNS for Dataflow.private and creates a record Kafka.dataflow.private pointing to 192.168.10.100. This allows applications to use a meaningful hostname. However, There is a caveat with DNS and PSC. If TechCorp's applications cache DNS responses and the PSC endpoint IP needs to change, they must manage the TTL carefully. Mike sets a 300-second TTL on the DNS record, balancing between DNS, query load and flexibility for changes. TechCorp's application team updates their Kafka clients to use kafka.dataflow.private on port 9092. They discover an interesting behavior. The Kafka protocol includes broker advertisements. When Kafka brokers advertise their addresses, they use their internal IPs, 10.10.0.x, which are not routable from TechCorp's VPC. This is a protocol-specific issue with PSC. To solve this, Dataflow must configure their Kafka brokers with advertised.listener settings that use the load balancer IP instead of individual broker IPs. This ensures Kafka clients receive the correct endpoint address. This kind of application-specific configuration is common when using PSC, with protocols that embed IP addresses. Monitoring and troubleshooting in production. Both companies implement comprehensive monitoring. Dataflow monitors the service attachment for connection count, rejected connections, and NAT subnet utilization. They set up alerts when the connection count approaches their limit of 10, or when NAT subnet IPs are nearly exhausted. They also monitor the underlying load balancer's health. TechCorp monitors the endpoint from their side. They use uptime checks targeting 192.168.10.100:9092 to detect any connectivity issues. They also implement VPC flow logs to track traffic patterns and troubleshoot any issues. Interestingly, they notice that all return traffic from the PSC endpoint shows a source IP of 192.168.10.100, even though it's actually coming from Dataflow's network. A real issue occurs when Dataflow performs maintenance on their Kafka cluster. As they drain nodes for updates, TechCorp experiences connection resets. This highlights an important point. PSC provides network connectivity, but application-level availability still depends on the underlying service. Dataflow implements better health checking and connection draining to minimize disruption. Another issue arises when TechCorp tries to connect from a different region. They have applications in US East 1 that need to access the service. They learn that PSC endpoints are regional. They need to create another endpoint in US East 1, but this fails because Dataflow's service attachment is only in US Central 1. This forces an architectural decision about multi-region deployment. As Dataflow acquires more customers, they need to scale their PSC setup. They have used 3 of their 16 NAT subnet IPs and are approaching their 10 connection limit. Sarah increases the connection limit to 50, which is a simple update command. However, she cannot shrink the limit below the current number of active connections, as Google prevents this to avoid disrupting existing connections. For the NAT subnet, they need more IPs. Sarah creates an additional NAT subnet, 10.10.101.0/28, and adds it to the service attachment. PSC can use multiple NAT subnets, automatically distributing connections across them. This is the recommended way to scale, rather than trying to expand existing subnets. Dataflow also implements consumer groups for better management. They create accept lists for different customer tiers: enterprise customers and standard customers. Enterprise customers get automatic approval while standard customers still require manual approval. This is managed through Cloud Resource Manager tags and IAM conditions. On the billing side, Dataflow discovers that PSC traffic between regions incurs standard inter-region egress charges. When TechCorp accesses the service from US East 1 after Dataflow expands there, Dataflow pays for egress from US Central 1 to US East 1. They factor this into their pricing model, charging different rates for same region versus cross-region access. After 6 months of production use, both companies have learned valuable lessons. Dataflow learned to provision NAT subnets generously. They now use /27 subnets, which provide 32 IPs each. They also learned to implement application-level health checks that PSC-connected clients can use, since network connectivity doesn't guarantee service availability. TechCorp learned the importance of endpoint IP management. They now use a dedicated subnet range for PSC endpoints to make firewall rules cleaner. They also implemented automated testing that verifies PSC connectivity during their CI/CD pipeline, catching issues before production deployment. Both companies documented critical operational procedures. How to diagnose connection issues by checking both sides' firewall rules first. How to handle the producer's maintenance windows by implementing retry logic in clients. And how to plan for disaster recovery, remembering that PSC endpoints can't fail over to different regions automatically. The most important lesson is that PSC is powerful but requires careful planning. IP addressing, firewall rules, application protocol compatibility, and regional limitations all need consideration. However, once properly configured, it provides secure, scalable, and maintainable private connectivity that would be much more complex with traditional methods like VPN or VPC peering. Thank you for your attendance. Please consider subscribing to the channel.